Next one. A country has finitely many towns, some of which are connected by roads. And any road connects just two towns, and not a town with itself, to be very pedantic. Each town flies a flag of a certain color. So here is an example. There are 1, 2, 3, 4, 5, 6, 7 towns. The segments are roads, and the colors are the colors of their flags. And just in case, I've also put the colors as letters inside them. So R is red, B is blue, Y is yellow. So that was an example of what we can have. And now, every once in a while, a revolution happens in a town C. What does this mean? This means that the flag of town C is recolored in the most popular color. So in the most popular color of T's neighbors. And I'll have to explain this a little bit more precisely because it is a bit of a, it is somewhat ambiguous in some ways. So you'll basically in town C, you look at the neighbors. For example, in the red town, the neighbors are yellow, yellow, and blue. And the most popular color among these neighbors is yellow. So in such a case, a revolution would turn this red flag into a yellow flag. So here is the fine print. If plurality of T's neighbors are flying the color C, and by plurality I mean for any color D that's not C, more of T's neighbors are flying color C than flying color D, then the flag of town C is recolored in color C. Some more fine print. In case of a tie, which means, so if several of T's neighbors, so basically if the most popular color among T's neighbors is not uniquely defined because there are several with the same popularity, then nothing happens. And also, if T's flag already is colored C, then nothing happens. Of course, recoloring in a color that you already have is pointless, and this does not count as a revolution. And last piece of fine print, revolutions do not happen simultaneously. This is important. If you allowed them to happen simultaneously, you would have a different problem in front of you with a different answer. So let me illustrate this by a sequence of revolutions. So here's an example. Here is one possible sequence of revolutions. So this is just a copy of this country. And now imagine a revolution happens in this yellow city here. The yellow city looks at its neighbors, which are blue and blue, and realizes that the most popular color there is blue. So it becomes blue as well. Next, the blue city here undergoes revolution. It looks at its neighbors, yellow, yellow, and blue, and it realizes that yellow is the most popular color. So it becomes yellow as well. And finally, the red city looks around and discovers that yellow is in fashion because yellow, yellow, and blue are its neighbors. So it becomes yellow too. And now, if you look at this country, it's stable. No city can undergo a revolution. This blue city, for example, its neighbors are yellow and blue. So this is a case of a tie. It's not like, I mean, both yellow and blue are most popular, but since there is two of them, the blue city cannot undergo a revolution. And similarly, everywhere else, the color that a city flies is already the most popular among its neighbors, or at least one of the most popular. Or to be more precise, if there are several most popular ones, it doesn't matter because in that case, revolutions cannot happen anyway. So much for the example. But now, here is a claim. Prove that revolutions cannot go on forever. So, in other words, after finitely many revolutions, no more revolutions will be possible. And I have seen this kind of problem being considered as a toy model of opinion dynamics. So you have a social networks and people adapt their opinions to those of their neighbors or friends or whatever it's called. It is not completely out of the blue. It's not just an artificial Olympiad problem, but I have seen this in Olympiads as well. So it's a dual use problem. Okay. Again, we're already kind of used to this. We're trying to prove that the process will end, so we're looking for a monovariant. What could a monovariant be? Well, when a town undergoes a revolution, I think I'm using town and city for the same thing here. So when a town undergoes a revolution, what it improves is, in a way, it gets more in line with its neighbors. So the amount of disagreement between neighbors decreases. If you understand disagreement to mean having different colors. And we can make this precise. Define a disagreeing couple to be a two-element set UV of two towns that are neighbors but are flying different colors. And you already see I'm saying couple, not pair. Why? Because pair for me is ordered pair, and this should be unordered. So my claim is now and I should also define the total disagreement. I think in the notes I speak of total discord, but the idea is the same. To be the number of disagreeing couples. This is a non-negative integer. And now I claim that every revolution decreases the total disagreement. And in the notes, I go over this in full detail with footnotes and many long sentences. Here, I will just leave it to you. Think about how a revolution affects disagreeing couples, which of them it affects, which of them get lost, which of them appear, and argue that more disagreeing couples are destroyed than new ones appear. And therefore, the total number of them decreases. Okay, and now recall infinite descent, by the way. This is the same idea. The total disagreement cannot keep decreasing indefinitely, since it is a non-negative integer. If you have a non-negative integer and it decreases and remains a non-negative integer, it has to decrease by at least one at each step. And then it's just a matter of time until it becomes negative, but it cannot become negative. So it cannot go on forever. Well, it is and has to remain a non-negative integer. So the revolutions cannot go on forever either. And we're done.